All right, let's talk about two incredibly powerful yet surprisingly simple techniques for supercharging array operations: prefix sums and difference arrays. If you've ever been in a coding interview, you know that making array problems run fast is everything. And these two should be some of the sharpest tools in your toolbox.
So let's kick things off with a classic problem. Imagine this. You've got a massive array, maybe a million numbers long, and you're getting bombarded with thousands of requests, each one asking for the sum of a different slice of that array. How do you pull that off and do it fast?
Well, the most obvious way to do this, the intuitive approach, it leads us straight into a trap I like to call the slow sum problem. It works, sure, but it's definitely not going to win any races.
So, what's the first thing that comes to mind? For every single query that comes in, you just loop through it, right? You start at the beginning of the range, you go to the end, and you add up the numbers one by one. It's simple, it's direct, and if you have thousands of these queries on a million-item array, you're going to have a bad time.
And here's the kicker. The reason this is a non-starter. Its time complexity is O of n for every single query, where n is how big the range is. In any situation where performance matters, like a coding challenge, that just won't fly. We need a way to get these answers instantly. But don't worry, there's a solution, and it's a really elegant one. Enter our first hero, the prefix sum array. The whole idea is to do a little bit of work up front, a pre-calculation, to make all our future queries lightning fast.
So what is a prefix sum array? The easiest way to think about it is like a running tally. We build this new array, let's call it P, where every spot in it holds the total sum of the original array up to that point. It's like we're creating a cache of sums ahead of time.
Okay, let's make this real with a quick example. Say this is our original array with just 4 numbers: 2, -1, 3, and 5.
So how do we get from that to this prefix sum array? Well, we usually stick a 0 at the beginning. Trust me, it makes the math way easier later. Then it's just a running total. 0 plus 2 gets you 2. Then 2 plus -1, that's 1. 1 plus 3 is 4. And finally, 4 plus 5 is 9. See? It's literally just the cumulative sum as we walk along the array.
And here is where the magic happens. Because we did that one-time bit of work up front, any future sum query becomes just a single subtraction. It's crazy. To get the sum from index L to R, you just grab P of R plus 1 and subtract P of L. That's it. So why does this work? Well, you're taking the grand total up to the end of your range, and then you're just chopping off the part you don't want, the sum of everything before your range started. What's left? Exactly the sum you needed.
And this is the huge payoff. We've taken an operation that was O of n and made it O of 1, constant time. I mean, it doesn't matter if your range is 10 numbers or 10 million, the time it takes is exactly the same. It's instant.
Okay, so prefix sums are awesome for a ton of queries. They're our go-to. But what happens when the problem flips on its head? What if instead of asking for sums, we need to perform lots and lots of updates?
Let's call this the mass update problem. Imagine you're told, hey, add 10 to every number from index 100 to 500, and then add 5 from index 2000 to 10,000. And you have to do this thousands of times. If you're using a prefix sum array, every single one of those updates forces you to rebuild the entire array. That's O of n every time. We're right back where we started. Too slow.
So for this, we need a different tool. And that brings us to our second hero technique, the difference array. It's practically tailor-made for this exact problem, handling tons and tons of range updates super efficiently.
So, a difference array. What's that? Instead of storing the actual numbers, or a running total, it stores the change between numbers. Think of it like storing the jumps you make to get from one element to the next. And the absolute genius of this is how simple an update is. If you want to add a value, let's say x, to a whole range from L to R, you only have to touch 2 spots in the difference array. Seriously, just 2. You add x at the very start of the range at DL. That kicks off the increase. And then, to stop that increase from continuing forever, you subtract x right after the range ends at dr plus 1. And that's it.
This is just incredible. Just like prefix sums gave us constant time queries, difference arrays give us O of 1, constant time, updates. It doesn't matter how big the range is, 2 tiny changes, and you're done.
Okay, so what's the catch? There's no catch, really.
just a different workflow. You do all your thousands of these super fast O of 1 updates on the difference array. Then, when it's all said and done and you actually need to see the final array, you just reconstruct it once. And how do you do that? You just run a prefix sum on the difference array. It's one final O of n pass to get your answer. So now we've got these two amazing tools: prefix sums for fast queries, difference arrays for fast updates. The big question is, when do you pull which one out of your toolbox?
Let's just lay it all out. If your problem is throwing tons of queries at you, but the data itself hardly ever changes, prefix sum is your champion, no question. O of 1 queries are unbeatable. But if the problem is the opposite, tons of updates, and you only need to look at the final result at the very end, difference array is the way to go. O of 1 updates are a game changer. And, what if you need both, a mix of queries and updates? Well, that's when you'd step up to a more advanced data structure, something like a segment tree, which gives you a nice balance, O of log n for both operations.
All right, before you dive in and start coding this up, a word of warning. There are a few classic traps that everyone falls into. I know I have. First, off by 1 errors. Be so careful with your array indexes, especially that r+1 in the difference array. It's so easy to mess that up. Double check if the problem is using 0-based or 1-based indexing. And a big one, if you're adding up a lot of numbers, make sure your variable type can handle it. You don't want an integer overflow to ruin your day.
So remember, next time you're in an interview and you see an array problem, just take a breath and ask yourself that one key question. Is this all about queries or is it all about updates? The answer will point you straight to the most elegant, most efficient solution.
And that really wraps it up. The big idea connecting both of these techniques is the power of pre-calculation, doing a little work up front to save a massive amount of work later. And it should get you thinking, what other slow, repetitive tasks could you make practically instant with a little bit of clever pre-calculation?